Welcome to Up Close, the research, opinion and analysis podcast from the University of Melbourne, Australia.
I'm Shane Huntington. Thanks for joining us. Early in the 20th century, when Ernest Rutherford and his students conducted experiments on the atom, they could not have known the extraordinary impact their work would have on society. Since the time of Rutherford's experiments, our knowledge of the atom and the subatomic world has expanded dramatically. Our understanding of the way our universe operates has fundamentally shifted, and we see the application of this knowledge almost everywhere we look in our daily lives, from power generation to medical diagnostics and cancer therapy. Radiation, a byproduct of atomic interactions, is often judged by events such as Japan's Fukushima Daiichi nuclear power accident in March 2011. But radiation in its many forms has also been harnessed to great benefit for human health and scientific endeavour. On Up Close today, Dr Roger Rasool joins us to discuss the physics of the atom and the causes and applications of radiation. Dr Rasool is a senior lecturer in the School of Physics here at the University of Melbourne, Australia. Welcome to Up Close, Roger.
Hi, Shane.
Roger, before we talk about radiation, I thought we might start with the world of the atom itself and just explore this a bit further. What are the main components that we find in the atom?
Well, we consider the atom to be probably the tiniest thing that society knows about. But when we look even further inside, we find other things in there. So it's probably better we get the sense of scale first. Now, maybe people can imagine under a microscope looking at a human hair or something like that. Well, that contains thousands and millions of atoms. So atoms are smaller than that tiny object, about 1/10,000th of a millionth of a metre. So it's pretty tiny. And if you get another atom, you put two of them together, you get a molecule. And then you keep building them up and you get a crystal.
And what's inside? You mentioned there are levels below what we think of as just the atom. What's inside there? What makes them up and what holds those components together?
Well, we're starting to reach into the things we call the fundamental forces of nature. The very first thing that probably they realised maybe 100 years ago when atoms started to be thought of scientifically was that atoms were either neutral or positively charged. Lovely you mentioned Rutherford and his students and all that. There was no internet, but these people all worked together and exchanged letters. And what they found out was that inside the atom were positive and negative charges. The positive charges were called protons and the negative charges electrons. And it was one of Rutherford's students, Chadwick, who postulated that maybe there were neutrons. And so the three objects, protons, neutrons and electrons.
You mentioned that the protons are all positively charged, so they want to repel each other. And the electrons are fine, they're all out in the wilderness somewhere. So what is it that's actually holding those protons together? You have the neutrons in there, but what's actually going on that allows that strong positive charge to be overcome?
Well, it's a force, and I suppose if we think of the sense of scale, to get those protons to be so close needs a very, very strong force. Now, physicists are very unimaginative, so we actually call it the strong force. And strangely, protons actually feel that force. And as we bring them together on that large scale of tens of metres, they repel each other, and they really repel each other. But strangely, when you bring them onto a scale of 1 over 1 with 15 zeros, so 10 to the minus 15, 10 to the minus 14 of a metre, suddenly when you bring a proton or a neutron close on that scale, that strong force takes over and binds the system together. It's at the heart of it, and it'll be quite important how that actually keeps the nucleus together, or in fact allows it to come apart or fall apart.
When we look at the periodic table and we see this whole range of different elements, and they all have completely different characteristics, although there are some consistencies between some of them, why are we getting this range of behaviour, and what's different between the elements when you talk about the atom in this way?
Well, around the late 1800s, early 1900s, the chemists were in charge because, in fact, atoms and how the electrons behave within the atoms was the key to the periodic table. In fact, as the chemists actually set up the periodic table, everything down the left-hand side of the periodic table blew up and everything on the right-hand side didn't blow up, and I suppose everything in the middle went from blowing up to not blowing up. Now, that sort of trivialises it, but what it really means is that as you add more and more charge into the atom, it seems like the properties change from being highly volatile to becoming completely inert. And I'll give you the two extreme examples. Hydrogen gas at one end, bang, and helium, completely inert, or a noble gas. Well, along comes physics and says, well, maybe we can start to explain this in the form of some predictive type of theory. And Schrödinger and other people came up, and Bohr and all that, with models in which we started to consider electrons closing in and forming shells. So the key to understanding the periodic table, I'm assuming we're referring to the chemical periodic table, is that it tells us a little bit about how the electrons are behaving around the positive charge of the nucleus.
It is hard to conceptualize and understand because, as we know, hydrogen and helium are consecutive elements in terms of the components that they have. So there's this massive change in their characteristics, even with that slight change in component?
Yes. The world is very subtle, I suppose, and slight changes are what allow us to exploit the chemistry of objects. And once again, it's the movement of charge. So I suppose so far inside atoms, we're now seeing that we've got charges, we've got forces that actually hold those charges, and the force that's holding that electron into the nucleus, that electric force, was very important also for Faraday and magnetism and electricity. That type of interaction all came about the same time. So there's a tremendous wealth of knowledge that comes around that 1900 early period there.
Now, many of our listeners will have heard the term isotope used. What is an isotope? How is it different from a standard atom of a particular element?
Well, let's pick another atom. Let's sort of think carbon. So we all know that carbon exists and we're all carbonaceous life forms. So what is carbon? So carbon, as far as we might be concerned, is 6 protons, 6 neutrons, and 6 electrons. That's what we call carbon-12. Now, the carbon-12 nature means that inside the nucleus, there are 12 objects which we call nucleons. So we don't differentiate the protons and neutrons as far as these nucleons are concerned. So carbon-12 means there are 12 objects in there and there are 6 electrons around the outside. So that's a neutral carbon atom. And what makes it carbon is the fact that it has 6 protons. So nitrogen has 7 protons. So that's the difference. So carbon can actually have some extra neutrons, which strangely doesn't seem to change its chemical properties, and yet may change other properties, and especially if we consider, say, carbon-14, where all of a sudden carbon goes from being this type of magnificent atom that just stays forever and forms diamonds and forms the fuel cycles that we have for society, suddenly becomes radioactive.
One of the interesting things is the fact that these different isotopes, although they do have the addition of another neutron, still have the same chemical properties.
Well, why don't we use our bodies, Shane, as the detector? I mentioned the carbon-12. We can also put carbon-11 into our bodies, and strangely, our bodies say, there's some carbon and it might be bound to something, and my body doesn't have a problem with that. Or I could have a different isotope of iodine, for instance. Iodine is really important in your body and your well-being. But imagine it's a particular isotope of iodine. It might get trapped into your thyroid or whatever, where iodine chooses to actually stop there. And if it's radioactive, we start to want to know, how is this radioactivity going to affect my body, and therefore what impact that might have. So our bodies tend to only differentiate chemicals, not isotopes.
Roger, when it comes to some of these atoms, the larger atoms we hear about and so forth, being unstable, what do we actually mean by that? What's the difference between an atom that is stable, that we see, in our everyday lives for a long, long time, and one that's not?
Well, let's define stability. If we grab an atom and it has so many protons, so many neutrons, and we come back 20 years later and we have a look at that atom and it still has the same number of protons and neutrons, well, we consider that stable. And in fact, for many years, everyone simply assumed matter was stable. And then Marie Curie made some great discoveries some 80, 100 years ago, that in fact matter isn't stable. And this is where chemistry really had some puzzlement about this whole process, because from a chemistry viewpoint, you mix two chemicals, you might make different types of compounds, but you rarely can change, lead to gold or whatever. But if we go back to protons and neutrons inside the nucleus, if you change a number of protons or change a number of neutrons inside the nucleus, you change an element. You may change it to a different isotope by just adding more neutrons. But imagine you remove a proton somehow, or a proton suddenly changes. Now, I'm being a little cagey here, Shane, but sometimes what we have in instability is, in fact, that a large nucleus chooses to spit out a few constituents. So whoever's in charge of this atom says, well, okay, 2 of you protons and 2 of you neutrons form together this helium nucleus, and you guys are out of here. And therefore, the mass of that atom changes, and that's called radioactivity. Another possibility is that the atom sort of says, well, listen, I seem to have too many neutrons or too many protons. Is there a mechanism by which a proton can turn into a neutron or a neutron turn into a proton? In physics, we call this beta decay. And in fact, once again, to introduce yet another force, so we've had the strong force, we've had the electric force, we now have this rather weak force, beta decay, which allows this for a proton or neutron to swap their identities and change. And so if indeed you have an element that has so many protons and one of those becomes a neutron, it changes its element.
Roger, the idea that these atoms are potentially decaying and giving off radiation in a variety of combinations implies that that radiation itself has a variety of forms.
Yep.
What sort of forms are we seeing and how do they differ?
Well, this is one of these nice things where simplicity comes into it. It's the alpha, beta and gamma. That's what most of the people will hear about. So alpha rays are helium atoms. So Rutherford used to throw helium atoms at gold foils. And so they were the rays that Rutherford used. So they were giving off the first thing called alpha particles. Betas, they're actually electrons, and they're a form of radiation. Now, they are massive objects, they're electrons. They actually weigh something, and they come in 2 flavors. So they come in a flavor of a negative electron, or they come in a flavor of an anti-electron, or a positive electron, or a positron. And then finally, there's another type of radiation, which is gamma radiation. And that is not dissimilar to X radiation or light. So often we talk of electromagnetic radiation. And when we refer to gamma radiation, we mean electromagnetic waves that come from the nucleus. So they tend to have very, very short wavelengths. They're much more energetic than X-rays.
This is Up Close, coming to you from the University of Melbourne, Australia. I'm Shane Huntington. Our guest today is Dr Roger Rasool, and we're discussing the physics of the atom and the causes and applications of radiation. Roger, I'd like to now focus on an element we've already spoken about somewhat, that we hear about daily, being carbon. For many years, carbon dating has been used to determine the age of a variety of objects. What form of carbon is actually used in this carbon dating process? And how do we go about determining the age of an object using carbon?
Such a simple process, Shane. Let's recap. So most of the carbon in this world is carbon-12. Now, when the universe was formed some time ago, there were different elements around, but many of those might have been radioactive or different isotopes of carbon, and most of those have decayed. But strangely, when we look around very, very closely with very sensitive equipment, we can find a significant amount of carbon-14. Now, the strange thing is carbon-14 is radioactive. And by radioactive, we mean that carbon-14 has a half-life. So in other words, if I have a small lump of carbon-14 and I come back after some time, I may find that half of it has decayed into something else. Let's not trouble ourselves with what it decays into, but let's just say that if we had a gram of carbon-14, after 5,760 years, I hope I've got the time right, somebody will undoubtedly check, you'd come back and only find half a gram of carbon-14. If you waited another 5,000 X years, you'd only have a quarter of a gram. But where's that carbon-14 come from? Because no matter how old we think the universe is, it shouldn't actually be around. And very careful examination of the complexity of the atmosphere reveals the following. The sun shines, and from sunlight, we have rather large, intensive cosmic rays that strike the upper atmosphere. And generally speaking, they're not too big a problem down on the surface because they're absorbed by the upper atmosphere. But if you recall, we live in an atmosphere of mainly nitrogen and oxygen, 80% nitrogen. Just so happens that when cosmic rays strike the atmosphere, they produce neutrons. the neutrons actually can get absorbed by the nitrogen in the upper atmosphere, and that nitrogen actually, in capturing the neutron, forms carbon-14. And so in the upper atmosphere, we end up with a fair bit of carbon-14. It's still tiny, but now we need to consider the biological breathing cycle of matter that's alive, and we're inhaling and exhaling carbon dioxide all the time. So it just so happens that if you look at a tree or something like that, the life cycle during the growth cycle means that you have a constant replenishment of carbonaceous material into that object, and part of that's carbon-14. So now comes the tricky bit, or the simple bit. The tricky bit is obviously to detect it, but let's pretend we've got massive amounts of detectors and we can do it easily. You cut that tree at that point and it stops breathing. At that point, that tree can no longer replace the carbon-14 that was being constantly topped up, and so you've now locked the ratio of carbon-12 to carbon-14. After some period of time, that ratio will change. We now play forward to modern day and we pick up a piece of paper or a piece of wood and we say, if I look at the ratio of carbon-14 to carbon-12 and then mathematically try to work out how I would have got that ratio back to the present day ratio, you can then get an estimate, knowing the half-life of carbon-14, for how old the object might at least be, or certainly the wood or the material or the paper from which it was made. Just so happens geologists are very clever people too, and there are many other elements with long half-lives too. There's uranium dating, and there's a whole variety of other dating techniques for very complex objects or those that are older.
I can imagine the context, the social context, everything else of this information also adds to the accuracy.
Well, that's a very important point you raise. Science can never be divorced from society and from context. I suppose where science is powerful is in its ability to make a quantitative statement. So I think in the case of the carbon-14, one can numerically justify the statement that is being made about the age of the object, but it is based on assumptions, and quite rightly so. Those assumptions become a little less objective and more subjective.
Roger, you've mentioned the various types of radiation that we see in nature and the way that radiation originates from atoms. Each of these types of radiation effectively, at some stage, interacts with matter once it leaves its point of origin. What does that interaction look like? What's actually occurring when we have a burst of radiation hitting other objects, whether it be people or physical objects?
Well, it could be exciting. You may not see it. In fact, you definitely won't see it with your eye, but you can actually visualize these things maybe with detectors. One of the questions you'd ask is that interaction of your body with radiation, is it good or bad for you? Well, it depends how you look at it. So imagine you've got a cancerous growth somewhere in your body. You could have a burst of radiation come onto that cancerous growth, and it may knock out all of the electrons or destroy some of the bonds in the molecules and everything else like that. That's quite advantageous because it actually destroys that cancerous cell. And so people who've had cancer might have had some sort of radiotherapy, and that's a very positive use of radiation. There's the other possibility, and as a physicist, I don't know very much biology, but I want to imagine, say, a DNA strand, and it's a very complex object of lots of molecules as far as I will visualize it. And imagine some radiation comes along and happens to interact with that DNA strand. It might actually break one of the links in that strand, cause some damage to the DNA, and therefore maybe cause an error in a DNA sequence and therefore possibly lead to a mutation. There are other possibilities with radiation for imaging. The very positive use of radiation, because it's penetrating, it can travel through flesh, maybe get interrupted by bones, and we can image. So all of these interactions involve radiation either stopping or passing through. When radiation stops, it deposits energy, and that can be good or problematic, and so it really depends whether you want the energy there.
Roger, we sometimes hear the terms soft and hard radiation. What's the difference between these two?
It's just the energy, Shane. Around the world now, we have these great objects called synchrotron light sources, and they're sources of X-rays. And when we talk of soft X-rays or hard X-rays, we're really talking about the energy of the X-rays or the inverse of the wavelength. So the longer the wavelength of the X-ray, the lower the energy, the softer it is. It might not penetrate too far. So I suppose the language there reinforces that the harder something is, the more deeply it can travel through matter.
When we consider all the issues of radiation, isotopes and so forth, we live in essentially a very stable atomic environment in a sense. Our planet is relatively unchanged in that sense for the majority of its existence. Is there a definite drive towards stability for all atoms? What is making them decay? What is the cause there?
Well, we've got to be really careful because there are big pushes right now to really understand the universe. And when we sort of say we live in this environment where everything is stable, we actually don't know why. Because we're not really sure from a physics viewpoint how come there is all this matter and no antimatter. And how come things are stable? Yes, generally speaking, they're stable because of the age of the Earth, certainly, or the universe in which we find ourselves. Anything that was unstable tends to have decayed away. So if we'd existed some time ago, it might have been a little fiery. But then there are bigger picture questions, and part of that is what you're alluding to, which is what is our understanding of matter within the universe? And recently we've suddenly come to realize that maybe we only know about 4% of the universe, and the other 96% we don't exactly know where that's coming from, but we're still in the process of trying to develop theories and understand that. Where we find ourselves now, the matter that we interact with tends to be stable. There is a little bit of instability in the concrete, in the potassium, in anyone that you live with. There might be a little bit of radioactivity. So it's all around, but it's very important for life because the genetic diversity in the material that we see has been developed through this environment. And so how we've grown is a product of the environment in which we find ourselves in.
You mentioned this issue of the genetics and the link between radiation and the way we've evolved. It sounds like we do exist in a radioactive environment to some degree. How problematic is that? Does it differ when we move to different parts of the globe, different altitudes and so forth?
Why life is so nice on Earth is because we've got this atmosphere. And we mentioned earlier maybe the cosmic rays coming through and all those issues. Well, the atmosphere tends to shield us from a lot of the problems of radiation. So the ultraviolet radiation, the cosmic radiation, we're shielded down here on the surface. So if you fly around in an aeroplane and you do it very regularly, you're exposed to much higher levels of radioactive dose. If you have basements in particular countries sometimes, the presence of radium and other elements tends to expose you to slightly more radioactive dose. And in fact, Shane, as we look around all over the Earth, we actually find that the background radiation changes, and with that changes certain issues of well-being and whatever. They are tiny numbers, but we've got to remember we have 6 billion people on this Earth, so you can actually study those effects ever so slightly.
What about in the home? Where do we see applications of radiation, for example, in the home or the workplace?
Well, let's actually walk into a typical home. The very first thing is maybe as you walked up and a light turned on, there was an electromagnetic radiation sensor that actually picked that up. So that might have been a radar wave. So it's a radio wave. We actually don't differentiate between the waves, because light itself can be a bit of radiation. So there we go. As the light turned on, you got a lot of infrared radiation, and that kept you warm and helped you see. You walked in, and if you look up in most Western households, you may see a little flashing light on the roof, and there's a smoke alarm in there. And that in itself has got a radioactive source. It's probably an americium or a californium source of radiation that came from a nuclear reactor somewhere. And that's saving many people's lives by emitting tiny amounts of radiation and using that to detect whether there's any smoke. As you walk into the kitchen, you will find a microwave oven, which uses microwave radiation to actually heat food. And of course, the traditional oven uses rather infrared radiation. If you visit your grandparents' home and you find an old CRT television set, hopefully we've got a little bit of life in this podcast and they're still around. Believe it or not, there'd be probably 20,000 volt X-rays being produced by that device. But fortunately, there's a large glass and a very thick absorber, which stops those X-rays being a problem. It's everywhere.
I'm Shane Huntington, and my guest today is Dr Roger Rasool. We're talking about the physics of the atom and the causes and applications of radiation here on Up Close, coming to you from the University of Melbourne, Australia. Roger, you mentioned smoke alarms, for example. It's hard for people to see what distinguishes the use of this knowledge in terms of radiation in a smoke alarm in comparison to a nuclear power plant. In one case, you have something you have to put a 9-volt battery into power, whereas in the other case, the atom itself is powering whole cities. What's the difference in terms of what's actually being used there in terms of the atom's characteristics?
Let's try and go back to where this radioactive material might have come from. And it most likely emerged from what we would call a research reactor or a production reactor, where uranium was split. People have heard of splitting the atom and creating energy. Well, let's try and see how we can visualize this. So it just so happens that if you take a particular isotope of uranium, and we won't get bogged down in whether it's U-236 or 238 or whatever, but uranium has a particular number of neutrons and a particular number of protons. So protons defined as uranium. One might ask the question, why are there so many neutrons? But why can't you add more neutrons and still call it uranium? And the fact is you can. And so you add an extra neutron and the uranium says, wow, I'm still uranium, but I really start to wonder why I've got so many neutrons, and it becomes possible for that uranium atom to break into two. And in breaking into two, some of the protons decide to go off with one fragment and some of the neutrons, and the other protons go off with the other fragment and some of the other neutrons. And they form these new radioactive decay elements at this point from the fission process, and we call that fission when we break things apart. And then it just so happens there are some spare neutrons because you don't need as many once you make these lighter elements. And if we recall, the initial instigating item was to actually put an extra neutron in to actually break this thing apart. Those spare neutrons can then go off and make other uranium atoms also break apart. If you control that process carefully, you have a fission reactor that works perfectly and therefore can be used to produce useful radioactive elements. And some of the radioactive elements could be strontium or yttrium and other elements that are then used for medical purposes for diagnosing illness with people. Also, in the process, you break these objects apart, they have energy, and so they're moving quickly. So if you surround that reaction with some water and try to slow the objects down that are being pushed off, the temperature of that water goes up. That temperature of the water can be used to make steam, and that steam itself can be used to drive a turbine, so it's not too far off making a power plant, and hence the whole process is interrelated. So the process that we use to make the radioactive elements for the smoke detector, for curing people in hospitals, for powering pacemakers, also can be used to make electricity.
Roger, just finally, you talk about the fission process that we see in reactors. How does that differ from the process of fusion that we see in the sun?
Once again, it's big and small, Shane. So if we start off with hydrogen as being the tiny atom, we need a lot of hydrogens to push them close together to have enough protons, to make it look like uranium. And that process of pushing things together is called fusion. This was one of the exciting things with physics, and it's around about the 1920s, 1930s, when they suddenly realized that you could push things together and get energy out. Now, that is really counterintuitive, but actually grabbing two protons and two neutrons, in other words, grabbing deuterium and pushing it together to make helium, releases energy. Grabbing uranium and having it break into two releases energy. Actually, if you start off with hydrogen and burn and make helium and then carbon and nitrogen and oxygen and keep pushing those things together, strangely, you release energy all the way up till you reach about iron, and then you don't get anything. In a similar way, if you take uranium and you break it apart and you form all these elements that are lighter than uranium, you end up around iron. So iron seems to be the most tightly bound, most stable element, and isn't it strange? Because we find it all over the place.
Dr Roger Rasool, Senior Lecturer in the School of Physics here at the University of Melbourne, Australia. Thank you for being our guest today on Up Close and giving us a better understanding of physics in the atom and the causes and applications of radiation.
Thanks, Shane. It's been most pleasurable.
Relevant links, a full transcript and more info on this episode can be found at our website at upclose.unimelb.edu.au. Up Close is a production of the University of Melbourne, Australia. This episode was recorded on Thursday, 12th of May, 2011. Our producers for this episode were Calvin Parham and Eric Van Bemmel. Audio engineering by Gavin Neighbour. Background research by Deani Lewis. Up Close is created by Eric Van Bemmel and Calvin Parham. I'm Shane Huntington. Until next time, goodbye.
You've been listening to Up Close. For more information, visit upclose.unimelb.edu.au. Copyright 2011, the University of Melbourne.